Welcome to our workshop paper on linear mixed effect modeling for hyperparameter optimization benchmarking. This work builds upon the foundation of Rietzler and Hagmann, published in 2022, which introduced the linear mixed effects model-based significance testing to natural language processing. We have applied these concepts to hyperparameter optimization, where robust and reliable significance testing is crucial for making data-driven, well-founded claims about algorithm performances. Starting with what sets LMEM-based testing apart from traditional methods, it does not involve statistical tests directly on the experimental data. Instead, by training a hierarchical linear model on the data, we create an implicit representation of the performances in the model and then estimate mean and variance of each algorithm from the model's parameters. The resulting distributions are fit for almost any statistical test, like the Tukey HSD test. But importantly, our experimental data does not have to adhere to any requirements, like being normally distributed. LMEMs are chosen as models because they naturally depict hierarchical structures within the data, which is a common scenario in HPO, where we normally encounter multiple algorithms evaluated across multiple tasks run for different training durations. These background factors are dealt with via random effects. Instead of fitting to all data equally, the random effect first corrects each group's deviation to obtain an unbiased general performance estimate. Generally, LMEM-based testing can serve as a drop-in replacement for traditional significance testing methods such as autorank, but it offers much more in terms of flexibility. For instance, LMEMs allow us to aggregate data across different benchmarks, runs, or even epochs, to boil down results to become both more interpretable and more meaningful. It's just a question of adding the variable to the model formula. To determine these formulas, LMEMs also enable model-based hypothesis testing. In this context, two models themselves represent hypotheses about the relationships within the data. The model's likelihoods are compared using the generalized likelihood ratio test, giving us a chi-squared testing distribution. As an example, we analyze the impact of random seeds on the performance. For the null hypothesis model, the loss is explained only by choice of algorithm, and for the alternative model, the loss is explained by the algorithm and by a random factor for the seed. The GLRT then determines whether the alternative model explains the data significantly better, taking the added complexity into account, so it has a higher likelihood. This modeling approach means that we use the formulas to build structured hypotheses about how different factors, such as algorithm settings or dataset characteristics, affect the performance. We propose the use of such tests as sanity checks, for example, to determine the relevance of a benchmark early on, therefore saving compute, or of course for building a good model to do significance testing itself. So we have built models that corrected for the influence of meta features, such as prior knowledge or specific characteristics of the datasets, which can profoundly influence the performances. But conversely, we can also use LMEMs to study the meta features themselves, as we did with the quality of the priors being given to the HPO algorithm prior band. By observing how different algorithms perform under each prior, we could assess their quality labels and recommend resampling in two cases, where we found insignificant differences between good and bad priors, here in blue and red. In conclusion, LMEM-based testing presents a flexible and promising approach to significance testing in HPO benchmarking, including a model-based hypothesis testing framework. When carefully documenting the models and methods used, this approach can clearly help to advance reproducibility in AutoML.